Hi there. I'm glad you found this little pocket of quiet tonight. Outside the edge of your thoughts, the world grows dim and soft, like a city seen from far, far away. In that hush, we can lean gently toward one of the strangest questions physics has ever asked. What really happens at the coldest temperature the universe allows, where motion itself seems to fade toward stillness? Together, we'll wander down into that deep cold past winter air, past frozen space, to a place nearly 460 degrees below zero on the Fahrenheit scale, where atoms slow, light changes character, and our everyday rules begin to loosen. We'll move slowly, like conversation between close friends, letting each idea arrive without hurry. If this kind of quiet wondering keeps you company, you're welcome to leave a soft like or subscribe so you can find your way back here again. For now, we'll just begin. Imagine the world being turned gently down to a softer setting, not just on a thermostat, but in a deeper way. Absolute zero isn't only a number on a scale. It's an idea that changes how you think about warmth and cold. When you hold a mug that's pleasantly warm, or when a draft of night air brushes past, it's easy to treat hot and cold as simple sensations. But what you are really touching is motion. Heat is motion, hidden and constant, living inside everything around you. Every bit of matter you know, air, skin, ceramic, metal, is made of particles that never quite sit still. They jostle and bump and sway in a restless dance too small for your eyes to see. When something is warmer, those particles move more wildly, bouncing and spinning with extra energy. When it's colder, they calm down, their motion softer and slower. The world you move through is full of this invisible dancing, all day, every day. Now, picture yourself turning a quiet dial, lowering that motion, not all at once, but gradually, like turning down the volume on a familiar song. The notes are still there, but they grow fainter. The dance of atoms continues, but with less and less energy. Keep lowering it, step by careful step, until the motion is almost gone, until everything feels close to a pause. In theory, there comes a point where that motion reaches its minimum, where the jiggling of particles is as quiet as nature will allow. That point has a name: absolute zero. On the Celsius scale, it sits at about 273.15 degrees, and on the Fahrenheit scale, it hovers around 459.67 degrees below zero. Those numbers are so extreme they hardly feel like weather anymore. They sound less like temperature and more like a challenge to the way reality works. They mark a cold deeper than any winter on Earth, colder than most of the empty stretches between the stars. And yet, for all their final sounding certainty, they describe a place we can never quite arrive at. The closer we push matter toward that deep cold, the more stubbornly the last traces of motion cling on. Absolute zero stays a little farther ahead, like a horizon that shifts every time you walk toward it. Even so, scientists have learned how to creep astonishingly close. Inside carefully shielded labs, using lasers, magnetic fields, and quiet tricks of physics, they coax atoms into slowing down more than you'd think possible. As they do, the world begins to behave in new ways. Atoms stop looking like separate, solid beads in our imagination and start behaving more like overlapping ripples in a single, invisible pond. Whole clouds of particles can slide into a shared quantum state called a Bose-Einstein condensate, where it becomes hard to say where one atom ends and another begins. They begin to move as if they are one quiet, unified thing. It isn't just colder, it's a different way of existing. In that realm, the familiar rules we rely on each day lose some of their grip, and the odd, delicate rules of the quantum world take over. These rules do not worry about everyday logic or common sense. They allow matter to be spread out and sharply defined at the same time, to behave like waves and particles at once. The temperature pressed down near the very bottom of possibility becomes more than a number. It feels like a doorway into the hidden machinery beneath the surface of reality. To feel the weight of that, it helps to look more gently at what temperature actually is. Long before anyone could write down an equation or build a thermometer, heat was something you simply felt. Fire on the skin, ice biting through fingers, sun on bare stone, wind slipping under a door. These were all stories told through sensation. No one suspected that these feelings were tied to invisible particles dancing faster or slower. Warmth was comfort, cold was hardship, and that was enough to know. Only when humans learned to measure heat, instead of just enduring it, did the true scale begin to reveal itself. Glass tubes with rising columns, carefully marked metal, devices that turned expansion and contraction into numbers. These were small beginnings, but as the measurements grew more precise, they pointed towards something unexpected. Hidden at the far end of the scale, far beyond the coldest winter anyone had ever survived, there seemed to be a limit, a boundary, a place you could approach but not pass. That buried endpoint became absolute zero, a kind of silence written into the language of physics. In that silence, particles lose some of the individuality they wear so comfortably at higher temperatures. The churning randomness that fills your everyday world quiets down. Instead of every atom jostling to its own rhythm, patterns begin to emerge. Order creeps in where chaos used to rule. Motion slows so much that even the idea of time starts to feel different. Time, after all, is one way of talking about change. This before, that after, something happening in between. If almost nothing is changing, if motion is nearly gone, then the usual feeling of time passing starts to blur at the edges. It's within that strange, nearly frozen calm that nature hides some of its most surprising behaviors. Liquids can turn into superfluids that flow without friction, slipping through narrow channels and around obstacles as if resistance has vanished. Metals can become superconductors, carrying electrical current with no energy lost along the way. Exotic quantum states appear, coaxed into existence in low-temperature labs scattered around the world. This is why people go to such lengths to build machines colder than the emptiness between galaxies. They are not simply trying to freeze things for the thrill of it. They are searching for that deep, quiet cold because the universe shows new faces there, aspects of itself that never appear in the warmer, noisier ranges where we usually live. In that focused chill, the background hum of thermal motion is turned down, and subtler patterns have room to emerge. Strange as it may seem, echoes of this icy frontier touch your life every day. The tiny chips nestled inside your phone and your computer rely on quantum behaviors that were first glimpsed and understood by cooling matter close to absolute zero. The precision of atomic clocks, the ones that keep navigation satellites synchronized so they can guide you across oceans and city streets, comes from tuning into delicate transitions in atoms, transitions whose understanding grew from this same world of deep cold, ideas that sound like they belong to tomorrow, quantum computers, new states of matter, careful tests of how the universe began and how it might end, are all shaped by what we learn when we gently lower temperature toward its theoretical floor. The more carefully we look at this extreme, unreachable cold, the more it stops feeling like an endpoint and starts looking like a mirror. In that mirror, we are not just looking at how cold things can get. We are looking at the limits of motion, the nature of energy, and the framework that reality uses to keep time and change in motion. The very phrase absolute zero has a kind of daring music to it, as if someone had once asked, "How far can we push this?" and refused to stop until they reached the edge. That edge sits at the familiar numbers, about 273 on the Celsius scale, 0 on the Kelvin scale, a place where no warmth seems to be left at all. And yet, it isn't simply another chilly milestone. It is where our usual idea of cold stops making sense, a border beyond which temperature, as we know it, can't really be pictured. As things cool, that unseen crowd of particles quiets, but the quiet is hard-won. Each step lower costs more effort than the last. There is no simple final rung on the ladder, no point where you can say, "Now everything has stopped." Scientists like Lord Kelvin helped uncover a deeper truth. If heat is motion, there must be a point where motion would be as low as it can possibly go, and that point defines the zero of the temperature scale that bears his name, not as a convenience, but as a boundary nature itself draws. The third law of thermodynamics tells us that as you approach this boundary, it becomes harder and harder to move forward. Cooling slows. The last scraps of motion cling to matter like whispers that refuse to fall fully silent. No matter how many clever tricks we invent, no matter how carefully we trap and chill and isolate, absolute zero remains just out of reach. Even so, approaching it has changed how we see everything above it. Near that floor, gases can collapse into one shared quantum identity. Metals can carry current without resistance, and fluids can flow in endless loops without ever running down. The existence of this unreachable cold tells us that all the restless energy of the universe leans toward a quiet resting place. It suggests a floor under the ceaseless motion we take for granted and invites a gentle question. If the universe could somehow reach that floor, what would time itself become? In a place where nothing moves enough to mark its passing? In carefully cooled rooms, matter is taken down to billionths of a degree above that boundary, and scientists watch as the familiar rules begin to loosen and fall away. They rewrite their understanding in the language of quantum mechanics, catching brief, shimmering glimpses of a universe that behaves very differently from the one outside your window. Through it all, absolute zero remains an idea more than a place, a clean, silent line that gives shape to the entire temperature scale above it. Every degree of warmth you have ever felt, every shiver, every sunlit afternoon, is measured upward from that imagined floor. A temperature that can never be reached still manages to anchor all the ones that can. In the quiet of the night, thinking about that deep, impossible cold can be a soft reminder that even the ordinary warmth around you belongs to a much larger story. And so, in our thoughts, we keep drifting downward along that story, step by gentle step, the way you might walk toward a horizon that always seems a little farther away than it looked a moment ago. Each new experiment, each careful round of cooling brings us closer to that silent floor, but never quite close enough to erase the tiny distance that remains. And in that distance, in that thin sliver of not quite, some of the most interesting things are hiding. If absolute zero or just another destination, a box to tick and leave behind. It would lose the strange pull that makes people spend whole lifetimes chasing it. Instead, it stays just out of reach, like a star you can see but never touch, quietly setting the conditions for everything that unfolds as we descend. The closer we slip toward it, the more the world we know begins to loosen and change shape. Not because the numbers on a thermometer are shrinking, but because each small step downward peels back another layer of reality we didn't know was there. Temperature stops feeling like something you could sense with your skin and becomes more like a quiet idea, a countdown into a place where the busy, restless energy of everyday life thins out towards silence. Think of what happens when you cool something in the world you know. A liquid thickens and moves more slowly. A piece of metal grows stiffer, more brittle. The air of a winter morning can feel dense and heavy on your face. Underneath those familiar changes, the same story is playing out. Motion is losing strength. The atoms and molecules that make up those things are not stopping. Not yet, but their jostling is softening. Their frantic pace easing toward a stillness that's hard to picture. Because true stillness is not something we have ever really met. Even in a room that seems perfectly calm, with walls steady and objects quiet on their shelves, the air is alive with motion. Molecules vibrate and collide. Your body hums with chemical reactions, tiny charges moving in nerves, small rearrangements of atoms in every cell. Every bit of you, every patch of space around you is trembling with the low, constant murmur of heat. As you imagine turning the temperature down toward absolute zero, that murmur begins to fade, not in a single dramatic moment, but in a long, slow surrender, a fraction of a degree at a time. With each step, the rules you are used to depending on bend a little more. Atoms stop behaving like solitary marbles rattling in a box and start to blur into one another's presence. The closer you push them to that limit, the less they act like separate objects, and the more they move together, as if the whole system were slipping into one shared rhythm. This isn't just a poetic image. In the deep cold along that descent, particles really do begin to lose their clear individuality. Their quantum states overlap and mingle until they become almost impossible to tell apart. Some physicists talk about this not so much as cooling, but as watching matter quietly collapse into unity. The many becomes, in some sense, one. Even the way we describe what is happening has to change. At the temperatures of ordinary life, even the rawest winter you have known, we can get away with the old, comforting picture. Heat as something smooth and continuous, something you can mark with a simple thermometer and explain with straightforward cause and effect. But near absolute zero, that picture breaks. The familiar equations start to mislead us. The language of more and less heat, of gentle sliding values, stops fitting what we see. Here, the quantum world takes over completely. Energy and motion no longer come in a flowing stream. They arrive in tiny, indivisible packets. It is as if the staircase of temperature, which looked so even from far away, is revealed up close to be made of uneven steps, some shallow, some suddenly steep, with gaps in between where nothing can change until enough energy is gathered for a jump. Cooling something from 10 degrees to 1 can feel straightforward. Cooling it from 1 degree to 1,000th of a degree becomes like trying to drag the universe uphill. Every bit of energy you remove becomes harder to take because there is less left that can be given up. The last scraps of heat cling stubbornly to matter, held tight by the structure of quantum states. Each step downward takes more effort than the step before, as though nature had woven a quiet resistance into the bottom of the scale, a soft but unbreakable defense against ever reaching that perfect zero. That resistance is part of what makes this journey so captivating, because the closer you come, the stranger the scenery becomes, and you start meeting behaviors that don't show up anywhere else in the universe, not in the hearts of stars, not in the crusts of planets, not in the comfortable middle temperatures where we spend our lives. In this deep, rarefied cold, helium turns into a superfluid that can creep up the sides of its container, ignoring gravity's usual pull, slipping through cracks that would stop any ordinary liquid. Atoms that would normally bounce around like a room full of unruly children suddenly seem to settle down and move in perfect coordination, as though an invisible conductor had lifted a hand and brought them into sync. Electrons, which usually waste a bit of energy as they move through metal, suddenly glide without resistance, forming currents that can circle in loops without fading, as if friction itself had quietly stepped aside. Each of these behaviors is a small reminder that this region of extreme cold is not just about a shrinking number on a scale. It is about stripping the universe down toward its barest patterns. When you peel away motion, when you let the noise of heat fall almost silent, you begin to see structures and rules that have been buried under that noise from the very beginning. And here is the strangest twist. The more you approach what sounds like ultimate emptiness, the more you notice that it is not empty at all. Beneath the fading motion, there is hidden order. Beneath the quiet, there are laws and patterns that only become visible when everything else has gone still enough. Absolute zero sounds like an ending, like a final blank wall at the bottom of the scale. But it behaves more like a beginning, a place where new kinds of order arise. That is part of why people keep chasing it. Every notch downward is not just about achieving a colder record. It is about lifting away one more veil from what we think of as normal and finding something older and deeper waiting underneath. If you continue to count down in your mind, you arrive at a point where motion doesn't just slow, it almost vanishes. Heat stops feeling like a sensation and starts looking like something you can watch unravel, thread by thread, if you have the right tools and enough patience. At the temperatures we live with, even in the most carefully chilled freezer or the sharpest, clearest winter air, atoms are still restless. They vibrate, they bump, they trade energy in collisions that never truly stop. That constant dance is what keeps the materials around you behaving in familiar ways. But pushed toward absolute zero, the steps of that dance grow farther and farther apart. Movements stretch out in time. The jostling fades until, to our imagination, it nearly dissolves. In that frozen world, an atom no longer shakes the way it once did. It sinks down toward its lowest possible energy, reaching a state where, in a classical picture, there would be nowhere left to go and nothing left to give up. And at that point, our usual rules simply do not apply. Stillness itself becomes a kind of motion, one that belongs to the quantum world, the quiet, underlying layer that has always been there, shaping everything without drawing attention to itself. At these unimaginably low temperatures, atoms stop acting like tiny billiard balls and start acting like spreading waves. Not waves of water you can see with your eyes, but waves of probability, soft clouds of maybe here, maybe there, overlapping with the clouds of other atoms nearby. When enough of them are cooled and crowded together, those waves merge. Out of that merging arises a Bose-Einstein condensate, a state of matter so far from everyday experience that it almost feels like a story instead of something you can trap in a laboratory. In that condensate, thousands or even millions of atoms cease to behave as individuals. They share a single quantum state, moving as though they have agreed to be different faces of the same thing. Picture a crowd in which no one steps out of line, where every motion is part of one perfect, shared gesture. That's how matter begins to move when it is pressed this close to absolute zero. Individuality melts away, and the entire system flows and shifts like a single, enormous particle. It's more than a curious trick of low-temperature physics. It is a rare glimpse of how reality behaves when all the usual noise has been drained off. When the universe is quiet enough, it shows you the patterns that are usually hidden beneath its own warmth. Yet even here, the stillness is not absolute. Deep in the heart of quantum theory lives something called zero-point energy, a rule that says no matter how cold you make something, no matter how nearly you empty it of heat, atoms can never be completely motionless. They always keep a faint shimmer of energy, a tiny, irreducible vibration that refuses to go away. It is as if the universe has written a gentle law that says nothing can ever be perfectly still, not entirely, not even for an instant. This quiet remainder is what keeps absolute zero from being anything more than a horizon. You can move toward it, closer and closer, but you can never cross over to the other side. The place where all motion would truly end simply is not available. That unreachable quality is exactly what turns absolute zero from a simple number into a quiet boundary in our understanding. It is defined as much by what cannot happen as by what can. So scientists keep building colder and colder machines, not because they expect to slip past that boundary, but because every small step nearer lets them explore the strange borderland between motion and stillness. Each new experiment reveals another way the world can behave when almost all of its heat has been drained away. In that borderland, superfluids glide without thickening, climbing and creeping in ways that look like defiance but are really just matter freed from friction. Superconductors carry currents without resistance, letting electricity loop without fading, guided not by magic but by quantum rules, finally taking center stage. In the hush, near absolute zero, the universe becomes both simpler and stranger. And for a while, you are allowed to see how much has been hidden inside the ordinary warmth of everyday life. And in that deep cold, some things begin to happen that sound almost like rumors from another universe. Electrons slip into loops of motion and circle forever without losing even the tiniest scrap of energy, as if the very idea of waste had been quietly erased. Currents that should fade simply do not. They keep going, calm and inexhaustible, following paths where resistance has fallen to zero. It feels impossible, and yet it unfolds here in our own world, simply because we've learned how to guide atoms to the brink of stillness and watch how they behave there. The closer we look, the more obvious it becomes that absolute zero is not a hard stop at the bottom of a chart. It is more like the outline of another kind of reality, waiting just beyond our reach. In that frozen quiet, even time begins to feel different. If collisions almost cease, if atoms merge into a shared existence where nothing jostles or rearranges in any way, we can easily see, what does it really mean to say that 1 second has passed and then another? How do you measure time when almost nothing changes between the ticks? Physicists don't so much answer that question as they move around it carefully, tracing its edges. Every time they peer more closely into this territory, another layer of the strange quiet peels back to reveal something new underneath. It starts to feel less and less like we are simply studying cold, and more like we are standing at the foundations of everything, listening. The deeper you descend in temperature, the closer you come to a place where heat loses its last footholds. Here, warmth is not just rare, it becomes impossible in the usual sense. Energy, that restless, invisible currency that drives every action you know, from the beating of a heart to the glow of a star, runs out of easy moves to make. It has been drained from nearly every jostle and vibration, leaving behind a kind of poised stillness. To understand why that matters, it helps to return to the quiet idea that heat is motion, not a glow, not a color, not even a sensation, but the relentless jiggling and colliding of atoms and molecules. Every bump, every tiny exchange of energy between them adds up to the temperature you feel when you wrap your hands around a mug or pull a blanket more closely over your shoulders. When you cool something, you are not just changing how it feels, you are slowly stealing energy from that dance. As you keep turning down the dial, you strip away more and more of that motion. There comes a point where there is no extra movement left to drain. The particles have slumped into their lowest possible state of energy, a kind of settled posture beneath which they cannot sink. At that point, the heat you've been cooling away doesn't have anywhere left to hide. In a very real sense, it no longer exists within that system. This is where the third law of thermodynamics rises up like a quiet, unbreakable boundary. It tells us that as you approach absolute zero, the energy you would need to remove to chase away the last remaining flickers of motion grows without limit. The cost of squeezing out that final shred of movement becomes impossibly large. No clever design, no stronger magnets, no brighter lasers can ever pay that price. The universe simply does not allow it. And yet, every step that falls short of zero is still a step into somewhere astonishing. As energy drains away and motion fades, what remains is not emptiness, but order. The wild, random collisions that fill the ordinary world settle into patterns. In that deep quiet, new behaviors appear, behaviors that cannot survive when heat is churning everything into chaos. Those exotic states we whisper about superfluids, superconductors, Bose-Einstein condensates, are not just party tricks of physics. They are examples of what matter does when heat has loosened its grip almost completely, when nearly all of the thermal agitation has been peeled away. The only thing left guiding atoms and electrons is the fine, exact machinery of quantum physics. Friction vanishes. Electric currents find paths that cost them nothing. Particles stop behaving like a crowd of separate individuals and begin to move as pieces of one continuous wave. All of this rests on a deeper question that stretches beyond numbers on a thermometer. If heat is motion, and motion is change, what becomes of time in a place where change is almost gone? At the edge of absolute zero, where energy has been pressed down to a whisper, and atoms are gathered into a kind of eerie stillness, time no longer feels like a river that carries events forward. It begins to resemble a frozen landscape you can look at from above, all at once, instead of a stream you are forced to ride. Of course, we never stand in that landscape. The zero-point energy woven into quantum mechanics won't allow anything to be truly, perfectly still. There is always a faint hum buried in the background, a minimum vibration that cannot be removed. Even at the very brink of nothingness, the universe refuses to be completely silent. That remaining shimmer is not the noisy motion of everyday heat. It is the smallest possible flicker of energy, a quiet signature of existence itself, written into the fabric of space and matter. That is why the end of heat is so compelling. It is not the end of matter, not the end of physics, but the point where our everyday picture gives way to something hidden. Rules that are usually drowned out by chaos become clear. Structures that were there all along step forward. So scientists build their extraordinary cooling machines and coax atoms to within billionths of a degree of absolute zero, not to win a contest for the coldest number, but to reach this quiet world where the ordinary dissolves and the quantum world takes over completely. In that hush, they can watch the universe behave in ways that once belonged only to thought experiments written in the margins of notebooks, waves of probability suddenly visible in the lab, currents that do not fade, fluids that ignore the usual drag. These are not just curiosities. They are the roots of technologies that shape your days, the principles that make sensitive instruments possible and help tiny circuits hum reliably in the background of your life. And if this is what happens when energy fades almost to nothing, the hint is that the next steps downward are stranger still. Below this boundary, the questions stop being mainly about temperature or motion and start to reach into the nature of existence itself. As heat drains out and motion nearly vanishes, the quantum world is no longer pushed into the background. It steps forward, steady and unavoidable, like someone who has been standing in the shadows waiting for the room to go quiet. In the warmth of ordinary life, quantum mechanics is always there, but you do not notice it. It is muffled by the sheer chaos of countless particles crashing and colliding, by the noisy shuffling of heat. That chaos hides the subtler rules that govern things on the smallest scales. But as the temperature falls and the collisions slow, the clutter of motion thins out. The whispers underneath become audible at last. Those whispers say that particles are not truly solid the way our hands expect them to be. They are not neatly separate, nor are they always where we think they are. Instead, they exist as overlapping clouds of possibility. When you remove almost all of their thermal energy, those clouds swell and begin to blend into one another until the line between this atom and that atom grows faint. Instead of many small, separate things, you begin to see one larger, connected thing. This is the world of quantum coherence, and it shows itself most clearly in the deep, frozen dark. Here, atoms do more than share space. They begin to share identity. When a cloud of atoms is cooled to within a billionth of a degree of absolute zero, it can collapse into a Bose-Einstein condensate, a single, unified quantum state. This is not a poetic flourish. It is a literal transformation. Those countless atoms move together as though they are one. They stop acting like independent pieces and instead behave like one enormous wave spreading across the entire system. You can no longer point to one spot and say, this is where one atom ends and the next begins, because that boundary has dissolved. In this darkness, quantum rules no longer have to compete with temperature. They take control. And when they do, the world looks alien to our normal instincts. Superfluids flow without resistance, ignoring the drag that would slow any ordinary liquid. Superconductors carry electrical currents that could, in principle, circle forever without losing energy. Quantum tunneling, where particles appear on the far side of barriers they do not seem to have enough energy to cross, becomes not a rare oddity, but a natural part of the landscape. This is why people go to such lengths to build elaborate cold traps and intricate magnetic fields. They are not trying to conquer cold as a prize. They are trying to hear these whispers clearly, to strip away everything that distracts from the most basic rules the universe follows. In that frozen silence, the cosmos reveals itself as less like a rigid machine and more like a fluid, probabilistic, interconnected web. In that web, particles influence one another in ways that defy the simple, straight-line logic we are used to. The quiet quantum world that emerges near absolute zero touches your life, even if you never see a superfluid or a condensate with your own eyes. Without the idea of absolute zero and the long, careful journey toward it, we might never have learned how to invite quantum mechanics into our tools and technologies. But there is something more than usefulness hidden here. There is a kind of philosophical softness to it, a sense that what we are really watching in these chilled experiments is reality changing the way it behaves. As heat drains away and the noise of motion falls quiet, the universe's most private rules begin to speak without interruption. The deeper you go, the quieter it becomes. Not quiet in the way of sound, but quiet in the sense that nothing moves unnecessarily, nothing happens by accident. Every remaining quiver of energy is shaped by structure, not by chance. The world in that regime becomes simpler and sharper, almost unnervingly perfect. And still, it is never utterly still. 0-point energy remains that faint, unavoidable hum that even the universe itself cannot erase. That hum matters. It's a quiet reminder that there is no such thing as complete emptiness, no place where existence collapses into absolute nothing. Even in this frozen dark, the universe keeps a small, enduring pulse, balanced delicately on the edge between motion and stillness. Stay with that image for a moment, and this deep, suspended state begins to feel different. Everything that once seemed separate starts to feel quietly connected. Boundaries that looked sharp at ordinary temperatures soften, and the more you sit with the thought, the more it feels as though absolute zero was never only about cold. It is about stripping the world down to its barest form. When almost all motion has been drained away, what remains is not just less heat, but a different way of being, as if reality has taken off a layer of disguise and is finally showing you its most honest, unadorned self. If these are only the whispers we hear just above absolute zero, it's hard not to wonder what else is waiting in that frozen world, slightly beyond our reach. We are not finished descending, not in imagination. There is more hidden beneath this quiet, more to see in the thin space where motion almost ends. If we keep following the trail, we might start to glimpse what it looks like when even entropy itself leans back and rests. Here, the descent stops feeling like a distant theory and starts to become something you could almost watch. At temperatures just a breath above absolute zero, matter changes into something so strange and so still that it hardly seems like the same substance that builds rocks and oceans and skin. This is the realm of Bose-Einstein condensates, where particles stop insisting on being separate and begin to merge into a single, ghostly state. Under ordinary conditions, every atom is its own tiny world. It spins, it vibrates, it drifts through space, carrying its own private energy. Even pressed together into a solid, each atom keeps its individuality, jostling and bouncing in its own slightly different way. Heat feeds this independence like a crowd of people all talking at once, no two conversations quite the same. Near absolute zero, that heat is patiently stripped away. Motion slows, the excess energy drains out, and what remains is not just colder, but simpler. The noisy, classical rules that work so well in everyday life begin to fade. In their place, the deep, invisible rules of quantum mechanics take over. Atoms stop behaving like little beads and begin to spread, to blur into gentle waves. Those waves overlap and start to lock together. It is no longer a million separate things. It is one thing, a Bose-Einstein condensate. This state of matter is unlike any other you encounter in daily life. Imagine again that crowded room, full of people walking, shifting, laughing, caught up in their own thoughts. That is matter at normal temperatures. Now imagine that without a command, without any outside force, every person slowly falls into step, moving with one shared intention, as if individuality has melted away into a single purpose. That is what happens inside a condensate. Millions of atoms merge into a single quantum identity. They move as one, exist as one. You can no longer point to a place and say, "This is where one atom ends and the next begins," because they have stopped being separate things at all. When this idea was first proposed, it sounded almost like a dream. In 1924, Satyendranath Bose and Albert Einstein asked what would happen if a collection of particles were cooled so far that the usual jostling could no longer drown out their quantum nature. They predicted that if you removed enough heat, the particles would all slide down into the very lowest energy state available and share it, forming a new kind of matter. For decades, that prediction stayed on paper. We simply didn't have the tools to cool anything that far. It wasn't until 1995 that a group of scientists finally coaxed a cloud of rubidium atoms down to just a few billionths of a degree above absolute zero. When they looked at what they had made, they found exactly what Bose and Einstein had described, an entirely new state of matter, moving like a single, unified ghost. Ghostly is not an exaggeration here. When you peer into a Bose-Einstein condensate with the right instruments, you don't see a cluster of distinct points. You see a smooth, shimmering cloud, a single entity where every atom is synchronized. It is as if matter has stopped arguing with itself and agreed to behave as one. In this state, matter can do things that sound impossible in the warmer world. A condensate can flow with no friction, gliding without losing energy to the usual bumps and tangles. It can interfere with itself like a beam of light, forming patterns that belong more to waves than to solid objects. It can exist in overlapping arrangements where here and there blur together. This is not the kind of matter that makes coffee cups and door frames and car engines. This is matter stripped down to its most fundamental, quietly unreal behavior, a fleeting glimpse of what the universe is built from when it is calm enough to show you. Yet for all its strangeness, this ghostly state is not just a curiosity sealed away in a laboratory. It is a key that unlocks some of the deepest rules of reality. By studying Bose-Einstein condensates, scientists are not simply learning how cold atoms behave. They are watching quantum mechanics play out on a scale large enough to see. They are learning how particles interact when individuality disappears, how waves of probability knit together into a single whole, and even how the very young universe might have behaved when everything was packed into a hot, dense, uniform state. In a quiet way, a condensate is like an echo from the beginning. When you cool matter this far down, you are forcing it into a state of almost perfect order. It may, in some small way, resemble what the cosmos looked like before structure formed, before galaxies, before stars, before the complicated tangle of events that eventually led to you lying here listening in the dark. It is as though, by chasing absolute zero, we are not only exploring the edge of temperature, but brushing our fingertips against the edge of time. That is why this state matters. It is a reminder that beneath the familiar world of warmth and motion lies a quieter, stranger universe that only comes into view when almost everything else has been stripped away. And even here, we are not finished. If Bose-Einstein condensates show us what happens when matter unites, the next step in our downward journey lets us glimpse what happens when even entropy, the great engine of disorder, begins to rest. The silence of the cold deepens into something stranger still. We have already watched atoms slow. We have followed matter as it merges into a single ghostly state and watched the everyday world dissolve into something more unified, more delicate. But if we imagine moving even closer to absolute zero, we meet a concept that has always been tied to the direction of time itself: entropy. Entropy is often described as the tendency of the universe to move from order toward disorder. It is why neat rooms get messy, why carefully stacked things tend to tumble, why a drop of ink spreads through water and never gathers itself neatly back into a drop again. It is why a cup that shatters on the floor stays broken. It is why, in your own life, the past feels fixed and the future feels open. Entropy grows, disorder spreads, and we move forward with it. Near absolute zero, this tide is almost brought to heel. When you cool a system to the edge of this unreachable temperature, something happens that does not occur anywhere else in nature. The random motion that drives disorder fades away. Collisions that scatter energy into every direction nearly stop. Instead, everything settles. Atoms line up in their lowest possible energy states with nowhere left to fall. The chaotic shuffle of heat is replaced by a stillness in which there are almost no moves left to make. This is why people sometimes say that absolute zero would be the point where entropy reaches its minimum. Not zero. Quantum mechanics will not allow that, but as low as it can possibly go. The faint hum of zero-point energy still lingers, the tiny, irreducible vibration of a universe that can never completely freeze. Compared to the storm of disorder in ordinary matter, though, it is almost nothing. In that limit, it is as if nearly all the disorder has drained away, leaving behind a quiet, carefully arranged structure. Matter rests as close to perfect order as the laws of physics will allow. This isn't just an elegant idea on paper. In laboratories where materials are cooled to billionths of a degree above absolute zero, scientists can watch entropy loosen its grip. They see particles falling into alignment, energy levels narrowing, until everything behaves as if the universe itself has paused to take a long, steady breath. A cloud of atoms that was once a noisy blur of random motion collapses into a condensate, moving as one unified wave. Superconductors switch into their flawless state, conducting electricity with no resistance at all. Superfluids begin to slide without friction, circling without slowing. These are not just specialized tricks. They are glimpses of a world where entropy no longer sets the rules. In these tiny, frozen corners, the universe stops drifting in its usual direction. For a moment, the arrow of time, tied so closely to the spreading of disorder, seems to soften. That thought carries something unsettling with it. If entropy is tied to our sense of time's flow, if the increase of disorder is what gives us a clear before and after, what does it mean to approach a place where entropy has almost nowhere left to climb? In this deep, frozen stillness, time feels less like a rushing current and more like a calm, frozen lake. Events stop tumbling over one another. They simply stand there together, like rocks resting on a silent shore. It is not that time disappears, but its movement loses the urgency we are used to. In this strange world near absolute zero, the universe looks less like it is racing forward and more like it is hovering on the edge of motion and change. And yet, even in this pause, quantum mechanics keeps its faint, necessary hum. That hum matters. If entropy could truly reach zero, if disorder could be erased entirely, every configuration of matter would be locked in place forever. There would be no new paths, no rearrangements, no surprises. The universe would become a perfect crystal of stillness. That never happens. There is always that whisper of energy, that small trace of motion, reminding us that nothing can be perfectly frozen. Perhaps that is what keeps the story going. Without that faint hum, there would be no change, no future, no unfolding of events at all. So, entropy never truly dies. It only slows down, settling into its quietest possible form. It waits in this deep cold, reduced to a bare ember, like the last glow of a candle in a long night. And in that soft, lingering light, we glimpse what the universe is built upon, a delicate balance between the relentless pull toward disorder and the silent boundary that forever holds it back. But even in this frozen calm, as eerie and complete as it feels, the descent isn't really over. Here, at the edge of entropy's rest, deeper questions wait quietly. If disorder has slowed almost to a standstill, what happens to time itself when the universe is this still? What does before and after really mean when matter is pressed this close to the edge of nothing? Beneath the slowing atoms, beneath the fading heat, beneath entropy itself, what has been hiding there all along is time. We spend our entire lives carried inside its current. It nudges us forward whether we are ready or not. It shapes our days, marks our birthdays, and threads our memories together into a story. But down here, near the bottom of the thermometer, time doesn't feel quite the same. It doesn't rush the way it does in the bright, noisy world of warmth and motion. It hangs differently, stretched and quiet, like something that has been turned almost all the way down. Time, in the way we usually think of it, depends on change. We notice it when things happen, when a clock hand moves, when the earth turns, when particles collide and swap tiny pieces of energy. Every tick is an event. Every moment is something shifting from one arrangement to another. But at temperatures near absolute zero, that constant shifting almost stops. Atoms that once danced wildly are pressed into their lowest energy states, their movement reduced to a faint, reluctant tremble. If you could somehow stand here not with your body, but with your imagination, you would find yourself in a kind of suspended world where the normal rhythm of events has thinned to the barest strand. The universe doesn't freeze, but it feels as though it is holding its breath. That raises a strange question. If almost nothing moves, does time still matter? Or does it simply sit here too, waiting patiently for something, anything, to happen? Physics has an answer, though it isn't one that makes everything simple. Time doesn't disappear, but it becomes more abstract. At these temperatures, what we call time is no longer a steady tick-tock. that every observer shares in the same way. It becomes tangled with energy and motion, with quantum rules that bend the neat lines we like to draw between then and now. Near absolute zero, that line grows thin. Events stop piling up in the usual way. Time seems to have less work to do. Quantum mechanics makes the picture even stranger. In this deep cold, where particles overlap and form shared states, the usual sense of cause leading to effect becomes blurry. When millions of atoms merge into a Bose-Einstein condensate, they no longer act like separate things marching through time one by one. Instead, they behave like a single quantum wave, existing all at once in one wide, shared state. Inside that wave, time isn't something you measure from one little particle to the next. It stretches across the whole system at once, as though the clock that counts it has become slower, softer, less local. This isn't just an idea on a chalkboard. In real experiments near absolute zero, processes that usually tick along with perfect regularity can stall. Chemical reactions that would finish in an instant at room temperature slow almost to nothing. Even quantum fluctuations, the jittering, unpredictable background activity that usually fills empty space, grow quieter, as if the universe itself has lowered its voice. It's not that time has vanished, it's that it has been emptied of its usual urgency, leaving behind a long, frozen moment where almost nothing happens at all. And that leads to an unsettling thought. If time slows this much for matter in such a frozen state, what does that say about the deep knot that ties time to heat? If the arrow of time is linked to entropy, to the spreading and unraveling of energy, what happens in a place where entropy has nearly nowhere left to climb? Some physicists suggest that under these conditions, time might not be something that flows on its own at all. Instead, it may simply be another word for change. And when change nearly disappears, time thins with it. That doesn't mean time dies at absolute zero. Even here, zero-point energy, the faint, unkillable hum of quantum motion, refuses to go away. That hum carries just enough activity to keep the universe from locking into perfect, eternal stillness. In a way, that leftover motion is what keeps time alive. Without it, there would be no difference between one moment and the next. No way to say that anything happens at all. Maybe that is the most fascinating thing about this frozen edge of existence. It doesn't erase time. It reveals it. It shows that time is not a rigid stage quietly running in the background, the same for everything and everyone. It is a property that depends on motion, on energy, on change. Strip those things away, and time thins out like air on a high mountain until only the faintest trace remains. If this is what happens to time near absolute zero, then another question rises naturally out of the quiet. Can that temperature itself ever truly be reached? Or is it a horizon that always stays just out of reach, no matter how far we travel down the scale? We have followed the thermometer downward in our minds, peeling away motion, draining heat, quieting the restless chaos of matter. Now we are standing at the edge of the coldest idea we have ever imagined. Absolute zero. A temperature so low it feels less like a measurement and more like a wall in the fabric of reality. The number has been written down for a long time, about minus 273 degrees on the Celsius scale, 0 Kelvin, the point where heat, in principle, would be gone. For centuries, that idea has tempted physicists like a quiet dare. If this is the bottom of the scale, could we ever actually touch it? When people tried to move closer, they found something strange. The nearer you come, the more the universe pushes back. It is as though absolute zero has been hidden behind an endless row of locked doors. The reason lies in one of the most unyielding laws we know, the third law of thermodynamics. It tells us that as you approach absolute zero, the amount of energy you would need to remove to cool something further grows without limit. Each tiny fraction of a degree costs more than the last. At first, cooling is easy. Take a warm object, and it gives up its heat gladly to something colder nearby. But as you move down, that warmth becomes harder to coax away. The particles inside cling to their last traces of motion, and stripping away that final sliver of energy becomes like trying to smooth out the last wrinkle in an endlessly crumpled sheet. The closer you get, the more stubborn it becomes. In that sense, reaching absolute zero is like chasing a horizon. You can walk toward it forever, and it will always stay ahead of you. You can slow atoms until their movement is so faint that their behavior barely resembles anything familiar. You can chill a cloud of particles to billionths of a degree above zero. But that final step, the one that would carry you all the way, is always missing. Even if you could imagine taking it, quantum mechanics would stand in the way. Near the bottom of the scale, 0-point energy becomes impossible to ignore. That faint, unremovable hum is the lowest level of energy any system can have. No matter how carefully you cool, you cannot erase it. It is built into the very fabric of reality. Even if every other kind of motion went still, that subtle vibration would remain, refusing to let the universe ever fully freeze. Yet this doesn't make the journey pointless. It makes it rich. Even though absolute zero itself is unreachable, the effort to move toward it has led to some of the most beautiful discoveries in physics. Along the way, we have uncovered states of matter that exist nowhere else. Bose, Einstein, condensates, superfluids, superconductors. They are living proof that as you drift closer to this limit, reality peels back its layers and shows you more of what has been hidden underneath all along. The technology built for this chase has reshaped the world in ways that are easy to forget. Laboratories now use lasers and magnetic traps to slow atoms until they move more gently than anything found naturally in the universe. We have created pockets of matter colder than the empty space between galaxies. In those places, we have been able to study quantum mechanics in its purest form, without the smearing influence of heat. Absolute zero, this unreachable horizon, is not just a frustration. It is also a kind of gift. It sets the boundary that defines everything else. Without it, temperature would be a direction without a destination, a concept without a clear anchor. Absolute zero pins the scale in place. It says, this is as low as the idea of heat can go, and by doing that, it gives meaning to every degree above it. There is something quietly comforting in that. It means there will always be one more step we can take downward, one more fraction of a degree to explore, one more discovery waiting in the vanishing space between the world we know and the horizon we cannot cross. The point is not to arrive and plant a flag at zero. The point is to keep moving closer, to keep peeling away noise and motion until the universe shows us what it looks like when it is as quiet as it can possibly be. We may never truly reach absolute zero, but every step toward it teaches us something profound about heat, about time, about order and disorder, and about the hidden structure of reality that quietly holds everything together while you lie here, listening in the dark, What we have been uncovering isn't only a story about cold, or energy, or even quantum tricks. It is also a story about the way the universe guards its deepest workings, revealing them slowly, one fraction of a degree at a time. Each step downward strips away a little more motion, a little more noise, and in doing so, uncovers another layer of structure that was always there, waiting. And once you see why there is a limit we can never cross, a natural question rises gently out of the quiet. What is it that holds that limit in place? What law keeps that final temperature forever out of reach? Somewhere at the bottom of this story, we meet the rule that draws the line in the cold. We have been watching temperature drain away, watching motion slow and energy fade. If you want to understand why absolute zero remains just beyond our fingertips, this is where it happens. It isn't bad luck, and it isn't that our machines are clumsy or incomplete. It is something written into the universe itself, the third law of thermodynamics. This law does not announce itself with drama. The first law tells you very clearly that energy cannot be created or destroyed. The second law gives you entropy, that steady drift toward disorder, the spreading out of heat and information. The third law is quieter. It whispers that as a system approaches absolute zero, the amount of work needed to cool it the rest of the way grows without limit. No matter how clever your design, no matter how delicate your technique, nature will always add one more thin wall between you and the last degree. You can see its trace in every experiment that walks down the thermometer. The first steps away from room temperature are easy. Touch something with ice, bathe it in liquid nitrogen, surround it with liquid helium, and its temperature falls quickly. But as you keep going, each fraction of a degree becomes harder to win. It's like trying to empty a glass of water, only to discover that no matter how carefully you pour, there is always a thin film clinging to the sides, refusing to leave. That final trace of energy is just as stubborn. The reason lives in entropy, near absolute zero. A system's entropy, its disorder slides toward a minimum. Particles settle into their lowest available energy states. There are fewer and fewer ways left for them to shuffle around. The random jostling that normally helps energy spread almost disappears. When there is no more randomness to drain, there is nothing left you can easily take away. You can press the system closer and closer to perfect order, but you will never quite erase that last sliver of motion. Here, quantum mechanics steps in and makes the third law even more absolute. Even in this deep freeze, there is zero-point energy, the unavoidable hum of the quantum world. It is what keeps atoms from ever becoming perfectly still. No matter how powerful your cooling methods, you cannot pluck that hum out. It isn't heat in the usual sense. It is not a kind of energy that you can bleed away. It is a built-in feature of reality itself. That is why absolute zero is described as a limit rather than a destination. You can move closer than anyone once believed, possible billionths of a degree above it, colder even than the emptiest stretches of deep space, but you will never quite arrive. The law doesn't bend, and yet that impossibility has turned into a kind of guiding star. The fact that we can never reach absolute zero is exactly what has driven some of the most remarkable achievements in physics. Cryogenic laboratories all over the world have treated this limit as an invitation. They use beams of laser light to nudge atoms into a slower and slower drift, magnetic traps to hold them almost in place, and evaporative cooling that lets the fastest atoms escape so that the ones left behind are calmer, colder, more settled. Each technique chips away at motion, pushing matter closer to the boundary they know they cannot cross. Every time we draw nearer, the universe responds by showing us something new. Without the third law standing in the background, we might never have discovered superconductivity, the perfect, silent flow of electricity without resistance. We might never have seen superfluids or Bose-Einstein condensates, where clouds of atoms stop behaving like separate individuals and begin to act like one seamless whole. We wouldn't have learned that friction can vanish, that entropy can pause, and that time itself seems to blur when motion is almost gone. This law doesn't just tell us no. It also says something gentle and profound about the universe. It tells us that there are limits we can lean toward, but never cross. It suggests that perfection, in this case, the perfect stillness of absolute zero, can exist as an idea, as a boundary, but not as a place you can stand. The universe allows you to approach as closely as you like, but it keeps one last step forever beyond reach, as if to remind you that there will always be something left to wonder about. In that sense, the third law doesn't simply block the way, it shapes the journey. It forces us to pay attention to what happens in the narrowing space between what is possible and what is forbidden. Inside that thin, frozen gap, some of the most beautiful discoveries have been made. If you linger there in your thoughts, just above the impossible, the landscape of physics looks very different from the one you know in daily life. This is the part of the cold where matter stops behaving like matter as we're used to thinking of it. Here, near the bottom of the thermometer, the familiar rules of the world begin to warp. We have already seen how the third law wraps an unbreakable wall around absolute zero. Even just above that wall, the behavior of nature no longer matches the simple logic of warm rooms and everyday objects. At comfortable temperatures, physics feels reassuring. Objects have clear edges. Heat moves predictably from warmer things to cooler ones. Particles bounce and collide like tiny billiard balls, giving us effects that are easy to picture. As you cool a system down, you strip that ordinary behavior away, one layer at a time. Eventually, there comes a point where almost nothing familiar is left. The quantum world takes over completely, and what you find there is a catalog of phenomena that have no counterpart in the sunlit version of reality. One of the strangest members of that catalog is superconductivity. At higher temperatures, electrical resistance is everywhere. Run a current through a wire, and its electrons scatter off the atoms that make up the material, bumping and zigzagging, spilling some of their energy as heat. As the wire is cooled, that scattering fades. Cool it far enough, and at a certain critical temperature, something quiet and extraordinary happens. The resistance does not just shrink, it falls to zero. Inside the material, electrons begin to pair up in delicate unions, moving together in perfect synchrony. These paired electrons glide through the crystal lattice without tripping, without colliding, without losing energy. A current started in such a material can, in principle, flow in a loop forever, never tiring, never slowing, as if the very idea of electrical friction has been written out of the script. Then there are superfluids, those uncanny liquids that appear when certain substances, like helium, are chilled to a tiny fraction of a degree above absolute zero. In this state, the fluid stops behaving like any ordinary liquid. It flows without viscosity, slipping through narrow channels and around obstacles without resistance. You can spin it, and instead of swirling into the familiar patterns you see in water, it forms quantized vortices, tiny, orderly whirlpools dictated by quantum rules. It can even creep up the walls of its container and spill over the edge, not because something is pushing it, but because in this bizarre, low-temperature world, the usual rules that keep liquids in their place are no longer in charge. In the same realm, Bose-Einstein condensates reveal matter in yet another unfamiliar light. Those ghostly clouds of atoms that merge into a single quantum state show us what it looks like when individuality melts away. Millions of atoms occupy the same lowest energy level, acting like one vast, unified particle. In that frozen domain, the difference between many and one begins to lose its meaning. And these examples are only a beginning. The deeper you look into this frozen frontier, the more exotic it becomes. Quantum tunneling, the phenomenon in which particles appear on the other side of barriers that, by ordinary reckoning, they should never be able to cross, grows more important. Down here, it is not just a rare curiosity. It becomes a common way for the world to move. Particles stop caring about the boundaries we expect to contain them. They slip through walls of energy the way a quiet thought slips through the rooms of your mind. Even time seems different in this place. At such low temperatures, with motion slowed and entropy reduced, events no longer unfold at the pace you instinctively expect. Processes that would normally finish in an instant chemical reactions, certain particle interactions, are drawn out, slowed, until they look almost paused. The universe in this regime is not gone. It is suspended, like a single soft frame, stretched across a canvas of stillness. What makes all of this even more remarkable is that we have not just imagined this frozen edge of physics, we have reached it in carefully tended laboratories. Scientists have cooled atoms to billionths of a degree above absolute zero, holding them in place with laser light and magnetic fields. In that deep freeze, they have watched the laws of nature flex in ways that earlier generations only guessed at. They have turned ordinary gases into quantum clouds, seen fluids slip free of friction, and coaxed electrons into endless, effortless flow. This bending of physics near absolute zero is not merely a curiosity to be admired and then forgotten. It is a window. It shows us what the universe looks like when the familiar layers are peeled away, when the noise of heat and random motion is finally quiet enough that only the most fundamental laws remain. In that stripped-down clarity, reality reveals a version of itself that is purer, stranger, and in its own way, deeply peaceful, like the hush that settles over everything just before sleep. Perhaps the most extraordinary thing about this deep, frozen realm is what it quietly suggests. If the universe can bend this way in the cold, if matter and energy can transform so completely when we press them toward stillness, what else might be hiding here? What other rules might be waiting to show themselves as we move closer to the ultimate limit? We're drifting into one of the strangest, most mesmerizing territories of the cold, where matter stops behaving like anything you've ever seen with your own eyes. This is where superfluids live, those uncanny liquids that glide without friction, climb walls, and flow in circles without ever seeming to tire. They're not just odd tricks from a physics lab. They are proof that the universe keeps a set of hidden rules that only reveal themselves when reality is pushed down toward the bottom of the thermometer. At first glance, a superfluid doesn't look like much. Take liquid helium as an example. Cooled to just a few degrees above absolute zero, it behaves like a normal liquid. It sloshes when you move the container. It has thickness and drag. You can stir it and watch it swirl in familiar patterns. But as you chill it further, to the very edge of that frozen frontier, something astonishing happens. At a certain critical temperature, close enough to absolute zero that most of the heat has been drained away, helium undergoes a sudden change. It stops acting like an ordinary fluid. Its viscosity, the subtle resistance that makes every liquid lean against motion just a little, drops to zero. The helium becomes a superfluid, and from that moment on, it moves in ways that feel almost impossible. Pour it into a cup, and it will not simply sit and settle. Given the chance, it will creep up the walls and slip over the rim, as though gravity's authority has faded. Set it spinning, and it will keep spinning, not for minutes or hours, but in principle, forever, because there is nothing left inside it to slow it down. No friction, no drag, no quiet bleeding away of energy. It's as if the very concept of stopping has been written out of its story. The explanation for this strange behavior doesn't live in the familiar world of splashing water and swirling coffee. It lies in the quantum world underneath. At these low temperatures, the helium atoms lose their sharp individuality. Their quantum waves overlap and lock together into a single, unified state, much like what happens in a Bose-Einstein condensate. Instead of each atom choosing its own path, they move collectively. The whole liquid flows as though it were one continuous entity. Because of this perfect quantum alignment, there is no internal scrambling left to create resistance, no scattering, no microscopic tug of war to turn ordered flow into random heat. At this scale, there simply is no mechanism left to make the liquid slow down. The result is a flow that can, in principle, continue endlessly, not because it somehow cheats energy, but because there is nothing available to waste that energy on. This frictionless motion is more than a neat laboratory stunt. It changes how we see the fabric of matter itself. It shows that in the deep cold, the universe is capable of sustaining states of almost perfect efficiency, where movement doesn't gradually dissolve into heat, but stays clean and organized. Compared to that, our everyday world of resistance and loss starts to look clumsy and rough. The same quiet principle appears again in superconductors, the materials that carry electric current without resistance. In warmer conditions, electrons traveling through a wire scatter off the atoms that form the metal, spilling energy as heat. When you cool the right materials far enough, those electrons pair up and move in step, gliding through the structure without colliding. Different substances, different details, but the same underlying rule. Near absolute zero, motion stops being messy. It becomes precise, ordered, almost perfectly choreographed. There is something profoundly hypnotic about that idea. We live in a universe where loss feels like the rule. Push a swing and it slows. Roll a ball and it comes to rest. Run electricity through a wire and it warms up as energy leaks away. Everything seems to pay a tax to friction and disorder. Yet down here, so close to absolute zero, those taxes vanish. A superfluid pushed into motion keeps going. A superconducting loop of current can circle endlessly, held aloft by quantum order rather than ground down by resistance. Hidden inside, this is a deeper suggestion. If friction can disappear under these conditions, if matter can move endlessly without wasting energy, what does that say about the most basic limits of the physical world? Maybe friction is not a fundamental feature at all, but a symptom of heat and chaos, something that shows up when particles are jostling and tumbling over one another in disarray. Strip away that chaos, and underneath you find a level of order that feels almost alien. And still, that alien order is not beyond our reach. We've touched it. We've cooled helium until it behaved like a climbing, creeping liquid that refuses to stay in its bowl. We've built superconducting circuits where currents could, in theory, last longer than the age of the universe. These experiments are more than curiosities. They are brief windows into what matter looks like when it sheds the limitations of our warm, noisy world. The closer we get to this kind of perfection, the more it feels as though we are peeling back a veil that was never really meant to be lifted. Superfluids and superconductors are not just rare oddities at the edge of a chart. They are reminders that beneath the constant buzz of heat, the universe holds a kind of flawless rhythm, a state where things no longer resist or decay in the ways we're used to. If that's what lives here at the edge of the cold, it's hard not to wonder what might be hiding just a fraction of a degree further down, near the faintest hum of motion the universe can sustain. While we have been following absolute zero downward in our laboratories, the universe has been keeping its own frozen secrets in the vast dark spaces between the stars. Space, for all its emptiness, is not truly empty. It has a temperature, a gentle chill, just a few degrees above absolute zero, and that temperature is the quiet backdrop against which everything else unfolds. It acts like a cosmic floor, the coldest natural stage spread across reality. Step away in your mind from the warmth of planets and the fierce glow of stars, and drift into the deep interstellar void. You find yourself wrapped in a darkness so complete it almost feels like a substance. There is no direct sunlight here, no comforting spill of heat from familiar worlds, only the faint, stretched out afterglow of the Big Bang itself. Over almost 14 billion years, that primordial fire has cooled and thinned until it lingers as a whisper of radiation at about 2.7 Kelvin, just a few degrees above absolute zero. This faint sea of microwaves, called the cosmic microwave background, fills the universe from one side to the other. It is the quiet temperature of space itself. If you could float there, far from every star, you would be surrounded by a cold so deep that any winter on Earth would feel warm by comparison. And even so, this is not absolute zero. Space, vast and seemingly empty, is still a bit too warm to be perfectly still. Those lingering photons, those tiny messengers from the dawn of time, keep the cosmos from ever reaching the very bottom of the scale. Even in the farthest, darkest stretches between galaxies, there is still motion, still energy gliding softly through the void. Yet there are places that come closer than most. In the shadowed folds of interstellar clouds, where dust and gas gather into dense, lightless knots, temperatures can fall to just a fraction of a degree above absolute zero. These are some of the coldest natural places we know of, cosmic laboratories where matter slows to an almost perfect hush. Inside those chilled regions, molecules drift so slowly that they can stick together in fragile clusters, assembling the first building blocks of new stars and planets. In that sense, they are like frozen cradles for creation, places where the absence of heat becomes an opening for structures to form. The universe uses this deep quiet not as an ending, but as a beginning. There are stranger corners still, near neutron stars and black holes, where gravity bends everything: space, light, even the ticking of time. In the deep shadows around these collapsed giants, there are pockets so empty of energy that their temperatures sink very close to nothing at all. And yet, even there, absolute zero never quite appears. Quantum mechanics still stands guard. Zero-point energy, the faint built-in hum of existence, keeps everything from ever truly stopping. Reality seems to carry a rule inside it that says nothing. Not even the coldest patch of space may be perfectly still. This is part of what makes absolute zero such a haunting presence in our thinking. It isn't just an unreachable number on a chart. It is a boundary that hangs everywhere, even in the emptiest parts of the cosmos. No matter how far you wander from the stars, no matter how deeply you drift into the black, you will never cross it. You will only brush close, feeling it in the silence of those last degrees where matter almost forgets how to move. And yet, those nearly frozen regions are anything but meaningless. They are where the universe slows down enough for us to glimpse its subtle ingredients. Astronomers point their instruments at these cold clouds when they want to study the chemistry of the early cosmos, because only there can fragile molecules survive long enough to tell their story. In a quiet way, these places form a bridge between what the universe once was and what it is becoming. Perhaps the most fascinating part of this cosmic cold is what it hints about the far future. If the universe keeps expanding, keeps letting its energy stretch thinner and thinner, its overall temperature will continue to fall. Stars will exhaust their fuel and go dark. Galaxies will fade. Collisions and bright events will become rarer. Over unimaginable spans of time, the restless motion of everything will dim until the cosmos is little more than a thin, cold echo of what it used to be. In that distant future, space as a whole will creep closer and closer to absolute zero, not in a single drop, but in a long, slow slide. We would not see absolute zero realized in one small flask or one laboratory corner, but approached everywhere at once. A universe hovering at the edge of stillness, spread across an endless horizon of cold. And even then, in that almost frozen night, zero-point energy would remain, the last quiet vibration that keeps existence from becoming perfectly, utterly still. Let's drift back now from the silent emptiness of space to somewhere much closer, yet almost as strange. Not a distant nebula or a lonely cloud of dust, but a quiet room on Earth filled with cables, metal, and light. Our own laboratories, where people have learned how to push matter closer to absolute zero than anywhere else we know in the universe. These places aren't just rooms with equipment. They are like careful sanctuaries of precision, built to strip away motion one fraction of a degree at a time, until the ordinary world fades and the hidden rules of reality start to become visible. If you could walk into one of these labs, you wouldn't find frosted walls or swirling clouds of frozen air like in a movie. Absolute cold doesn't look dramatic from the outside. Instead, you'd see compact chambers of polished metal, vacuum pumps humming softly, tangles of cables feeding power and information, and beams from invisible lasers quietly crossing paths. Magnetic coils would wrap around parts of the setup, holding matter in place as if gravity had been gently rewritten. These are the instruments of the coldest work humans have ever done. The journey downward begins in a simple way, by cutting off contact with everything else. To cool something deeply, you must first let it be alone. Scientists pump almost all the air out of a chamber, creating a vacuum so empty that outer space would almost seem busy by comparison. With almost no stray molecules left, there is little to bang into the atoms they are trying to cool, little to carry warmth back in. Then they turn to liquids far colder than ice, liquid nitrogen, and then liquid helium to draw the temperature down further, to tens of degrees above absolute zero. Then, just a handful. For most of our everyday experience, that would already be unimaginably cold. But in these rooms, it's barely the first step. From there, the descent slows because each move closer to absolute zero becomes harder than the last. So, the tools have to become stranger. Lasers, which we often think of as sources of heat and cutting power, are turned into instruments of cooling. By tuning a laser to just the right color, scientists make its photons push against atoms that are moving toward the beam. Each tiny nudge slows the atoms down, like a gentle hand catching a rolling ball again and again until it nearly stops. With this laser cooling, atoms can be brought to temperatures within billionths of a degree of absolute zero, a realm so cold it doesn't occur naturally, not even in the emptiest reaches of deep space. But even that isn't the end. Once the atoms are slowed, they must be cradled in place so stray vibrations and fields can't easily warm them. Magnetic and optical traps form invisible bowls that hold the atoms gently, suspending them in space. Then comes another quiet trick: evaporative cooling. Just as the warmest molecules in a cup of coffee escape as steam, leaving the liquid cooler behind, scientists allow the most energetic atoms to leak out of their trap. The ones that remain are slower, calmer, colder. They repeat this again and again, shaving off the hottest atoms until only the quietest remain. With each cycle, the cloud of atoms grows more subdued, more synchronized, until what is left is no longer just a gas in the usual sense. This is how Bose-Einstein condensates are born in those small, humming rooms. It is how superfluids are created in controlled settings, how superconductivity is watched unfold not as a theory, but as a changing signal on an instrument. In these laboratories, quantum mechanics is not just an equation on a page. It becomes something you can almost see, in the way a ghostly cloud brightens on a screen or shifts in response to a tiny change in a magnetic field. These spaces are the closest things we have to windows into another version of the universe, one where heat and motion and even time seem to loosen their grip. And all this effort doesn't only satisfy curiosity. By chasing the lowest temperatures, people have quietly reshaped technology. The strong, detailed images from MRI machines, the delicate behavior of superconducting circuits, the first fragile steps of quantum computers, and the ultra-precise ticking of atomic clocks, all of them lean on ideas and techniques that came from these cold rooms. In trying to understand matter near absolute zero, we've not only uncovered deeper rules, we've started to build tools that rely on those rules. Still, no matter how far the temperature falls, the third law of thermodynamics remains there, like a calm, immovable line. Absolute zero stays just beyond reach, a horizon that seems almost to smile at every new record we set. But there is a quiet gift hidden in that refusal. Each time scientists take even the tiniest step closer, the universe offers something new in return: a fresh state of matter, a new quantum effect, a sharper glimpse of how reality behaves when almost everything has been stripped away except its barest structure. If you could stand beside one of these experiments and look at a cloud of atoms cooled nearly to absolute zero, you'd see something that feels more like a dream than like ordinary matter. A faint, softly glowing blur held in place by magnetic fields and light, resting at a temperature where motion has almost stopped, but not completely. The atoms blur into one another's presence, becoming less like a crowd of separate points and more like pieces of a single, quiet wave. It is not just cold, it is a stillness that somehow feels alive. From here, we can let ourselves drift even further into the deep quiet, to a place where one of the strangest behaviors of the universe begins to dominate: quantum tunneling. This is where particles stop paying attention to the boundaries we expect them to respect, where walls and barriers lose their simple meaning, and matter reveals a side of itself that feels almost like a magic trick written straight into the laws of nature. In the world you know, boundaries are reassuring. Throw a ball at a wall and it bounces back. Try to climb a hill without enough energy and you slide down again. That logic feels simple and solid. But at the quantum level, the rules soften. Particles do not behave like tiny, solid beads rolling through space. They behave like waves spreading, overlapping, and fading instead of sitting in one exact place. And waves can do something surprising. They can seep into places that classical rules would forbid. When a quantum wave meets a barrier, it doesn't simply slam against it and stop. Part of it can leak through. There is always a small chance that what we call a particle will be found on the other side, even if, by classical standards, it didn't have enough energy to cross. This is quantum tunneling. Most of the time, the chance is tiny. In the warm, noisy world where everything is shaking and colliding, those little probabilities are drowned out by chaos. But in the frozen stillness near absolute zero, where almost all thermal motion has been stripped away, those small chances no longer hide so easily. The particles are no longer endlessly jostled by heat. They settle into their lowest energy states, and their quantum nature comes into clear focus. Their wave-like behavior dominates. Instead of acting like individual marbles, they smear out into probability clouds. When those clouds brush up against a barrier, a portion seeps through, not as a metaphor, but as an actual, measurable event. That is, tunneling. In ultra-cold labs, where atoms are held in delicate lattices made of intersecting beams of light, scientists have watched this happen. Atoms that seem to be pinned in place in one side of the lattice are suddenly found in another, as though they have slipped through the walls that surrounded them. They have not climbed over in any way our everyday minds would recognize. They have simply appeared where, classically, they shouldn't be. It isn't that the atoms are breaking the rules. It's that we are finally seeing the deeper rules that were there all along. Tunneling is not a small, decorative detail in the universe's design. It is one of the keys that makes the universe work at all. The fusion reactions that keep the sun shining depend on it. Protons in the hot, dense core of a star do not actually have enough classical energy to slam together and fuse as often as they do. Quantum tunneling gives them a way to slip through the barrier between them and join. Without tunneling, the stars would be dim or lifeless. Without tunneling, the long chain of events that led to planets, chemistry, and life would never have had a chance to begin. Near absolute zero, tunneling becomes even more central. In superconductors, pairs of electrons called Cooper pairs can tunnel through barriers inside a material without effort, forming currents that flow without resistance. In the delicate circuits of quantum computers, tunneling is carefully used and guided so that particles can occupy and leave states in ways that classical physics would forbid. At this temperature scale, tunneling is not a rare exception. It is part of the main story. All of this can leave you with a strange feeling about what is real. At ordinary temperatures, it is easy to believe that the world is solid and definite. Things stay where they are put. Barriers hold them back. Time moves in a simple line, but near absolute zero, that comforting solidity loosens. Particles do not just move from here to there along neat paths. They exist as possibilities spread out in space, and sometimes they appear in places where you never expected them, not because they cheated, but because that was always one of the paths the universe quietly allowed. The deeper you follow this descent, the more it feels as though you are stepping out of the loud, bright world you know and into a quieter one that has been running underneath it the whole time, hidden by the noise of heat and motion. Here, near absolute zero, that noise has been almost entirely turned down. The whispers of the quantum world are no longer drowned out. They are the only voice left, soft and strange and endlessly patient, waiting to be heard. In the middle of all this talk about atoms and stars and frozen laboratories, a quieter question eventually appears. What about life itself? What would happen if something living could wander this far down the scale into the edge of frozen reality, where motion slows, energy fades, and the rules we know seem to loosen? We've watched atoms near absolute zero lose their individuality, slip into shared quantum states, and tunnel through barriers as if the ordinary world were only a sketch. But somewhere behind all of that is a stranger thought. What if our kind of life, built out of warmth and motion, could ever touch this place? Life as we know it is made of movement. Every cell in your body relies on reactions that never truly stop. Proteins fold and unfold. Enzymes link molecules together and pull them apart. Ions flow in tiny currents across membranes. The faint electrical murmurs in your brain, the contraction of heart muscle, the slow work of repair in each tissue, all of it depends on energy sliding from one arrangement to another. Heat is woven into that process. Even when you rest, even when you sleep, life is never entirely still. It hums with motion. Now imagine turning that motion down, not just to the bite of a winter night or the sting of liquid nitrogen, but far below that, toward the silent edge near absolute zero. As the temperature falls, the reactions that make thought and heartbeat possible begin to lag. Each step of chemistry takes longer. Signals that usually race through a cell slow to a crawl. Below a certain threshold, they stop. The machinery of life is not built for this kind of stillness. For beings like us, the descent toward absolute zero is not just about cold. It is about crossing the limit where activity can continue at all. And yet, in another sense, we already brush against this boundary. In cryogenic science, researchers cool biological material to temperatures where almost nothing changes. Not living people, but cells, embryos, tissues, even whole organs are brought to very low temperatures to preserve them. By slowing their inner motion enough, they suspend decay and delay the unraveling that would happen at ordinary warmth. It is not life as we usually mean it. It is something in between, a long pause, a kind of artificial stillness that can last for years. These temperatures are far from absolute zero, but they echo the same principle. The colder something is, the slower the biological clock ticks. In theory, if you could cool a living system without damaging its structure, you could approach a kind of stasis. No aging, no decay, almost no movement forward in time. But what would it mean to push this further? If you could bring a living system all the way down to the edge of absolute zero without breaking it, would it still be alive in any meaningful sense? Or would it become something else entirely? Would it just be frozen matter, indistinguishable from its surroundings until warmth returned? Or would it exist in some strange limbo, suspended in the same ghostly quiet, where even time seems to lose its urgency? Experiments with single atoms and tiny clusters of particles give us hints. Physicists have cooled individual atoms and molecules to near absolute zero and watched them fall into near perfect quantum coherence. behaving as one unified wave. But life is not a single particle. It is a tangled web of processes, all dependent on motion and exchange. If you drain that motion away completely, you are not just pausing life, you are removing the very distinction between living and non-living. The carefully organized dance dissolves into the same quiet matter that everything else is made from. Maybe that is part of why this question feels so heavy. Absolute zero is not only a theoretical limit on temperature, it is a place where the dividing line between alive and inert begins to blur. It reminds us that, at a fundamental level, living systems are patterns in motion. Strip the motion away, and what remains is arrangement without activity, structure without story. In practice, our bodies and cells cannot reach that edge intact, but something else can. The particles themselves. When they are cooled this far, they do not just slow down. They become so quiet that their remaining motion feels less like movement and more like a soft shimmer underneath everything. In the world you know, nothing ever sits completely still. A rock in your hand feels calm, but its atoms vibrate in place. Its electrons move through their clouds, every constituent humming with a low background of thermal energy. That gentle agitation is what we call temperature. At the edge of absolute zero, that agitation almost disappears. Vibrations shrink, collisions fade. Motion becomes so small that, compared to everyday life, it might as well be absent. What is left is a kind of order that feels foreign to our warm intuition, matter reduced to the simplest, least restless version of itself. But even here, the silence is not perfect. No matter how deeply you cool a system, you cannot empty it of energy entirely. 0-point energy remains, that faint, unavoidable hum built into quantum mechanics. It is the minimum motion the universe allows. Even in the coldest imaginable place, the cosmos refuses to be completely mute. Compared to the restless world above, this hum is different. It is not the noise of disorder. It is the soft tone of reality at its lowest volume. Look at matter in this state, and you see the world stripped to its framework. Particles are no longer bouncing at random. Their behavior is synchronized, governed almost entirely by quantum rules. It is the quiet of a system that has been emptied of almost everything except its most fundamental laws. In that quiet, matter begins to reveal things that stay hidden at higher temperatures. Boundaries between particles start to blur. Bose-Einstein condensates appear not as rare exceptions, but as natural outcomes of the conditions. Millions of atoms, once independent and noisy, collapse into a single quantum identity. The usual individuality of matter, its tendency to exist as countless separate pieces, is replaced by an eerie unity. It is no longer a crowd, but one extended, quiet entity. Within that unity, strange behaviors become normal. Fluids that would usually resist motion lose all friction. Electrons stop scattering and flow in loops that can last indefinitely. Barriers that would normally block particles lose their grip as tunneling takes over. It can feel as though the laws of motion have been rewritten, but in truth, we have simply moved far enough down the scale to see the deeper version that was always there, beneath heat and randomness. And then there is time. When movement slows, when collisions fade and entropy approaches its floor, time begins to feel different. It is not erased, but it stretches into something pale and thin. The distinction between before and after softens. Down here, in the silence of particles, Time does not rush past like a river. It lingers, like air in a closed, quiet room. It feels less like a flow and more like a deep, still pool. That is why this silence matters. It is not just an extreme condition to record in a notebook. It is a way of seeing the universe without all the extra motion layered on top. When scientists create these ultra-cold states, they are not just cooling atoms for sport. They are peeling the world back to its skeleton, to the underlying structure exposed by the absence of heat. And that structure is anything but empty. It is dense with information. In this regime, quantum mechanics speaks the loudest. The smallest, strangest rules of the universe stop being background corrections and start becoming the whole story. Here we learn what matter really is when it is not endlessly stirred, what energy really means when there is almost none left to trade, and what remains when we strip away nearly everything that feels familiar. If this is what happens when particles fall quiet, then it becomes natural to ask a deeper question that has been hiding underneath our whole journey. What is temperature, really? What do we mean when we talk about cold and heat, about approaching absolute zero? If, at the bottom of the scale, silence and motion blend into something that no longer fits our everyday words, it is worth pausing to look directly at the idea itself. We have been speaking of cold and warmth, of motion and stillness, of particles slowing until they nearly stop. But what does temperature actually measure? What is it telling us when we say something is at a certain number of degrees or a certain number of kelvins? Why does this simple seeming quantity lead us into the foundations of how the universe behaves? At its heart, temperature is not about the numbers on a dial or the feeling on your skin. It is about motion, microscopic motion. It is the measure of that invisible dance of atoms and molecules as they move, vibrate, collide, and trade energy. When something is warm, it means those particles are rushing more quickly, crashing into each other more often, and with more force. When something is cold, they are moving more slowly. On one level, that is all it is, a way to describe how lively or quiet that hidden dance has become. And yet, when you follow that motion downward and take it away step by step, you eventually arrive at a boundary, a place where the particles can hardly slow further because there is almost no motion left to remove. That is absolute zero, the point where temperature, as a measure of motion, hits its theoretical floor. There is nothing left to give. This is what makes absolute zero such a powerful idea. It is not just the coldest possible number. It is the bottom of motion itself. Once you see that, you begin to understand why temperature connects so deeply to everything else, from the way stars burn, to the one-way flow of time, to the quiet quantum effects that only stand out in the frozen dark. Temperature is not only about how fast individual particles move, it is also about how they share energy. In a hot object, energy is spread chaotically. Molecules crash together, exchanging speed and direction in a constant shuffle. That chaos is what we experience as heat. Cool the object, and those collisions slow. The exchanges become less frequent, and patterns begin to show through the noise. As you go lower still, that order becomes dominant. Near absolute zero, instead of countless particles each acting on its own, you see collective behavior. Atoms and electrons begin to act together as if they are parts of one larger entity. That is what happens in Bose-Einstein condensates, in superconductors, In superfluids, temperature becomes more than just a measure of how fast. It becomes a threshold, marking the point where ordinary matter gives way to something entirely different, new phases and new rules that were waiting underneath all along. When scientists cool something to a billionth of a degree above absolute zero, they're not just making it colder, they're creating a different kind of environment, one where the usual rules begin to fold in on themselves. In that world, temperature stops feeling like a simple line on a scale and starts to look more like a key. Turn it low enough, and doors open into phenomena that stay hidden at any other point on the thermometer. Temperature is tied to entropy, that quiet measure of disorder we visited before. As temperature falls, entropy usually falls with it. The lower you go, the fewer ways the particles in a system can shuffle themselves around. At absolute zero, in the ideal, entropy reaches its minimum because there is no spare motion left to stir up randomness. The system is not just cold, it is almost perfectly ordered, stripped of every unnecessary detail. That is why the bizarre quantum effects down here stand out so clearly. The noise has been turned down, and what remains is the bare structure of reality. But temperature isn't only a property of matter, it touches information as well. Physicists studying black holes have learned that even these extreme objects, places where matter is compressed beyond recognition, can be described using temperature and entropy, as though they too had a kind of heat and a measure of hidden information. The same ideas that tell you how warm your coffee is can, astonishingly, also describe the deep physics of the universe's most intense, mysterious structures. Seen that way, temperature isn't just about cold or heat. It is a language, a way of speaking about how energy moves, how matter behaves, and how order and disorder shape everything. When we talk about absolute zero, we are not just talking about a number. We are talking about the floor beneath that language, the ultimate stillness against which every kind of motion is measured. If temperature is really about motion, energy, and information, it's hard not to wonder what happens as the entire universe keeps cooling. Not just a flask in a lab, but everything. Every star, every planet, every stray particle drifting through the dark. What would it mean for all of that to sink toward the same silent floor? To feel that question, you can gently lift your gaze from the small experiments on Earth and imagine the universe as a whole. Space is expanding. The distance between galaxies is stretching, a quiet swelling of the fabric of reality itself. As it does, the leftover glow from the Big Bang, the cosmic microwave background, keeps cooling. Long ago, that light was searing. Today, it has softened to a faint bath of radiation, just a few degrees above absolute zero. If expansion continues, it will keep fading over unimaginable spans of time. The stars that burn now will not burn forever. Big suns will exhaust their fuel and die in collapses or explosions, leaving behind black holes or dense remnants. Smaller stars will slowly dim into embers and then into cold, dark husks. Black holes, after feeding on what they can, are expected to leak energy through Hawking radiation, shrinking so slowly that the timescales defy our usual sense of duration, and eventually disappearing. What remains after all of that is a universe that is almost completely dark. No shining stars, no glowing galaxies, only a thin mist of particles and faint fields spread across a vast, stretched out space. Those remaining particles will keep cooling, their interactions becoming rarer, their exchanges of energy weaker, until almost nothing happens at all. It is a future of freezing emptiness, in which all usable energy has been spent and there is no more work left for the cosmos to do. And still, even then, that final temperature will remain out of reach, just as in our laboratories, where the third law of thermodynamics quietly holds the line. The universe itself is bound by the same rule. Absolute zero will always sit a little beyond what can be reached. Particles will continue to carry their zero-point energy, that faint, irreducible hum of quantum motion that can never be entirely erased. There will be no heat as we usually understand it, no life, no familiar movement, but there will still be that last whisper of existence, a tiny vibration at the foundation of what is. In such a frozen future, time would become something almost unrecognizable, without stars to shine or burn out, without heat flowing from place to place. Time would cease to feel like a river carrying events along. It would flatten into a nearly featureless stillness, where nothing changes because nothing is left that can change. The universe would not end with a blaze or a sudden collapse, but with a settling into quiet. Even in that stark picture, there is a strange calm. The rules that let the universe blaze with young stars are the same ones that promise, far in the future, a long rest. And if the cosmos truly keeps drifting this way, another question begins to glow softly at the edge of thought. What happens to the laws themselves when they are pushed so far into the deep cold? We have already seen that near absolute zero, physics in the lab changes its face. Atoms stop behaving like isolated marbles and collapse into unified quantum states. Friction fades. Currents flow without resistance. Tunneling ceases to be a rare curiosity and becomes a central actor. These aren't just odd behaviors. They are hints that the warm, classical version of physics is only a thin surface layer. Beneath it lies something older, more abstract, less tied to the boundaries our senses prefer. Imagine that kind of physics not in a small chamber on Earth, but stretched across everything. As the universe cools, energy thins out and bright structures disappear. The cosmos would become dominated by the rules of the cold. Quantum mechanics would no longer be a set of guidelines reserved for tiny scales. It would be the everyday language of what remains. Without heat to drown it, quantum coherence could stretch across enormous distances. Matter might settle into quiet configurations of fields and waves. Time, too, would be reshaped. If the arrow of time is tied to entropy growing, then in a universe this cold, where entropy barely changes, time would no longer feel like a steady forward march. It wouldn't vanish. Zero-point energy would still be there, giving existence its thin pulse, but it might become more like a backdrop than a flow. Some physicists have wondered whether, in such extreme conditions, new forms of order might appear. There may be states of matter or structures of energy that cannot survive in the hot, noisy youth of the universe, but could emerge in the calm of its age. In that sense, the deep cold wouldn't just be an ending, it would also be a kind of unveiling. Heat hides the foundations of reality. Motion covers up the stillness underneath. As the universe cools and those layers thin, what is left is whatever has been there all along, expressed in its purest form. It might not look anything like the world you know, but it would be built from the same underlying rules, finally revealed without the distraction of constant change. This is part of why absolute zero, even though it can never be reached, has such a pull on the imagination. It isn't only the absence of heat, it is a threshold. Come close to it, and you stop seeing the universe the way everyday life trains you to see it. You begin to see the universe the way it is when everything unnecessary has been peeled away. Following the cold downward, we have moved in our thoughts from the restless motion of atoms to the quiet shimmer of zero-point energy. We have watched matter dissolve into ghost-like collective states, seen time lose much of its urgency, and imagined a cosmos where even stars and galaxies have faded into a long, soft silence. There is no further down to go, only a stillness so deep that it feels less like an ending and more like the baseline that has always been there, underneath every beginning. This is the stillness of almost nothing, not emptiness, not absence, but the plain, steady ground of reality itself. At the unreachable edge of absolute zero, there is no heat left to spill, no extra motion left to smooth away. Every atom has settled into its lowest possible state. Entropy has been pared down to its faintest murmur. What remains is not lifeless. It is simply quiet. If you could stand there in imagination, not with a body, but with a calm awareness, you would not see anything hurrying. You would not hear anything changing. Time would stretch until it hardly seemed to move at all. And in that frozen stillness, the universe would look different, not because some new thing had appeared, but because all the layers of motion and noise that usually cover it had finally fallen away. You would see the calm foundation on which everything else has always rested. There is a kind of comfort in that thought. Absolute zero is not just the bottom of a scale. It is a reminder that beneath all the burning and swirling, beneath the noise of life and the churning of stars, there is a deeper order, a quiet background that persists even when everything bright has gone out. We will never arrive there. The third law of thermodynamics will keep that edge forever, a little farther away, the way a horizon always stays just beyond the spot where you are standing. Yet that distance is part of its beauty. It means there is always another step to take, another fraction of a degree to explore, another hidden pattern waiting in the cold. Thought of this way, absolute zero is not truly an ending. It is the quiet that underlies every beginning, the soft silence that has always been in the background while everything else moves, grows, and fades. Even if we never touch it, it gives shape to everything above it, the warmth of your own body, the fire of the stars, the heat of the universe's first moments. Here, at the bottom of the thermometer in our thoughts, there is no more motion left to slow, no more heat left to lose, only the deep, steady hum of reality at its quietest, holding everything together while it rests. If you let yourself settle into that idea for a while, you may feel a small echo of that quiet inside yourself too, a kind of calm that doesn't hurry, doesn't demand, doesn't reach. It simply is.